Hello. For this lecture, we're going to be skipping ahead to Chapter 6, Section 4, and talking about the central limit theorem. The concept of this section is really just defining and applying what we call the central limit theorem. And it allows us to use the normal distribution to talk about, instead of finding the probability of one value being larger than or less than a given data point, it will allow us to find the probability that the average or the mean of a group of people have a probability of being larger or smaller than a given data point. And so here's the main theorem. The central limit theorem states that for all samples of size n, the distribution of the mean x bar, right here, can be approximated by a normal distribution with mean mu and standard deviation sigma over square root of n, right? And so no matter what the no matter what the original distribution is, if I want to talk about the average of that sample of x bar, I can approximate that distribution with a normal distribution with a given mean mu and a slightly standard or slightly different standard deviation, sigma over square root of n. So how do we use the central limit theorem in applications? What we're going to have is, for a population that has a normal distribution or a sample size greater than 30, the mean of our approximated normal distribution is equal to the original mean of the distribution. The standard deviation of our subsample is almost exactly the standard deviation of the original sample. But what we have is this correction distribution. We have to take sigma over the square root of n. And no matter what type of distribution we have, we're going to get an approximate normal distribution. And just like we've worked in section 6.2, we're going to need to find the z-score to translate that normal distribution into a standard normal distribution. And so that z-score calculation is going to be z is equal to x bar minus mu over that sigma divided by square root of n. Another way we can think about that formula is going to be x bar minus mu sub x bar divided by sigma sub x bar. This formula I do like because it keeps the same original structure of the z-score formula, but it translates it for this grouping of problems, and we'll see exactly how to do a problem like this. When we solve these types of problems, where we use the central limit theorem, one thing we have to distinguish is whether we're trying to find the probability that an individual value is greater than a data point, or the mean of a group of those samples are greater than a data point. Because the z-score we compute will be slightly different depending on if we want an individual value or a mean, right? If I want the probability that an individual value is larger or smaller or between a data point, I'm going to use my original z-score formula, where z is equal to x minus mu over sigma. However, if I'm considering whether the mean from the sample values is larger, smaller, or falls in between two data points, I want to use my new adjusted z-score, right there, where z is equal to x bar minus mu all over sigma divided by root n. And again, we said another way we can think about this formula is going to be x bar minus mu of x bar over sigma of x bar. And we have to remember that if we're going to use the second formula, that mu of x bar is really just the mean of my population. And that sigma of x bar is still sigma over the square root of n. And so there's really no difference between these formulas, although this one looks more like the standard original z-score formula. So I tend to prefer using this one. But again, we just have to remember that mu in that formula is my original mu, And this sigma sub x bar is not my original sigma. It's the one right over here. It's the sigma divided by the original sigma divided by square root of n. Okay, let's look at an example of how this works. Here, we want to look at the safe loading weight of elevators. And suppose that the elevator at a car rental building at an airport states that it has a maximum capacity of 4,000 pounds or a certain number of passengers. Here we'll say 27 passengers. And so what we can do is you can say, well, what needs to be the mean weight? I can divide 4,000 by 27 and get a mean weight of 148 pounds when the elevator is full. What we get to assume is that adult males are normally distributed with a mean weight of 198 pounds, or I'm sorry, 189 pounds, and a standard deviation of 39 pounds. What that tells us is the mean of our original distribution is 189, and the standard deviation of our original distribution is 39. So part A says find the probability that one randomly selected adult male has a weight greater than 148 pounds. And the second says find the probability that a sample of 27 randomly selected males has a mean weight greater than 148 pounds. And so these will follow those two cases that we talked about, right? Are we dealing with the probability of an individual or the probability of a sample? And if we look at part A, because it says one randomly selected individual, this deals obviously with the individual. So we treat this the way we treated normally distributed random variables in section 6.2 in the first lesson. For part B, because it says I have a sample of 27 randomly selected adults that have a mean weight greater, that tells me I need the central limit theorem for this, that I'm going to have a mean weight point of 148 pounds. So let's go through this and see how we actually compute this. So in part A, I want the probability that a randomly selected person has a weight greater than 148 pounds. Right? Again, this is any standard deviation, so I want to convert this to a normal distribution. I use my regular z-score value. I get 148 minus 189 divided by 39. And if I compute this and round to two decimal places, I get negative 1.05. So this now corresponds to the probability that a standard normal random variable is greater than negative 1.05. If I were to draw this, here's my mean of 0. That means negative 1.05 would be about there, and I want to be greater than that. Well, if I look at that, I know that my standard table does not tell me the area to the right, it tells me the area to the left. So to compute this probability, I will have to do 1 minus the probability that z is less than negative 1.05, right? Finding the probability that z is less than negative 1.05 is equivalent to finding the area to the left, which is exactly what our table tells us. So let's quick look at our table. Here I have my table, and again, my z-score I'm looking for is negative 1.05. So I have negative 1.0 and my 0.05. So I look all the way down and I look across. That is my value. That is the probability that z is less than negative 1.05 and is 0.1469. And I can use that in my problem. Okay, so I found that probability, and I'll plug that in, and I'll subtract that number from 1. If I compute that in my calculator, I'll get 0.8531. So the probability that a single adult weighs more than 148 pounds is the probability of 0.8531. Let's move on to part B, right? Part B asked if I have a sample of 27 people, what's the probability that the mean weight is greater than 148 pounds? And we said because it's asking about a sample of 27 people, that I have to use the central limit theorem. And all that states is if I want to convert this probability of a mean weight of 148 pounds to some standard being greater than some z-score, what I'm going to have to do is I can't use my original z-score formula. I use the central limit theorem version of our z-score, right? Where mu of the average is the original mu, and the standard deviation of my sampling is the original standard deviation divided by the square root of n. So let's compute those two things. Well, that's still the same mean of 189 pounds. Our standard deviation of the sample is going to be my standard deviation divided by the square root of 27. If I compute that, I'm going to get 7.5056. We'll keep this to a little more than 2 decimals because we want to get a complete answer. So let's compute my z-score. If I look to compute this, I get my central limit theorem version of z-score. And so I'll have my 148 pounds minus my sampling average, which is 189, divided by my adjusted standard deviation, which was 7.5056. And if I compute that and round to 2 decimal places, because now we're dealing with a z-score, I'll get negative 5.46. And I want the probability that z is greater than this new z-score, negative 5.46. Again, if I draw that with my standard normal distribution, negative 5 is going to be pretty far down that left side. I want the probability it's greater than. Again, this is an area to the right. And just as we've done before, to compute this area to the right, what do I have to do? Well, I have to do 1 minus the area to the left. So the probability that z is less than this 5.46. And this value will come from my table. So let's check on the table and see what the probability that z is less than negative 5.46 is going to be. Here, I notice I want my z-score to be negative 5.46. So what I want to do is look at the negative 5.4 row on my chart. If I start to look up, I notice there is no negative 5.4 value. And so what do? If I look at this very top z-score, it says, what if I have negative 3.5 or lower? And it turns out that if our z-score is low enough, I don't have to look for anything. I can just assume that the probability to the left is just that small, 0.0001. So we can say that our probability of negative 5.46 is going to be 0.0001. We can take that value back over to our problem and finish this solution. Okay, let's finish this solution. I found the probability that z is less than negative 5.47, and I get 0.0001. I can take 1 minus that and get 0.9999. So the probability that a group of any 27 randomly selected adults, that their average weight is going to be larger than this. That is a pretty high probability. That is almost 1. All right, so what can we take away from this? Right? We have a pretty good probability that an individual male will weigh more than 148 pounds, but there is an almost 1 probability that 27 randomly selected males will have a mean weight. That means that we can almost never have 27 males in this elevator, that we will almost surely exceed the weight of this elevator. And so, what can this help us do? Right? We want to introduce this idea of hypothesis testing. This idea of hypothesis testing is going to come up in chapters 8 and 9, so we would like to talk about it now. And in hypothesis testing, we are given some sort of hypothesis, and we want to check the validity of that hypothesis. Okay, so the one example that we've used kind of over and over again is this idea of body temperature, right? The assumption, the thing that we've always been told, is that the body has a mean temperature of 98.6 degrees Fahrenheit. And we have through data that the standard deviation is about 0.62 degrees. And if a sample size of 106 people are randomly taken, we want to find the probability of getting a mean of lower than 98.2 degrees. So what's the probability of getting a mean lower than that? And that's what we're going to compute. And so if we do this, because we're talking about a sample and a mean, this points to using the central limit theorem. So let's solve this problem. Okay, we're taking a group, a sample of 106 people. The mean of our original sample is 98.6 degrees with an original standard deviation of 0.62. I want to find the probability that the average of these 106 people have a body temperature of 98.2 degrees or lower. So because I'm dealing with an average, that means I want the z-score from the central limit theorem. Right? And again, mu of x bar, mu of our sample is just mu, and the standard deviation of our sample is the original standard deviation divided by the square root of n. So we can compute this. Right? Mu of x bar, that's going to be my original mu, that's 98.6. Our new standard deviation is going to be 0.62 divided by the square root of 106. And if I do this and keep a certain level of digits rounded, I'm going to get 0.0602. So I can compute the z-score. So 98.2 minus 98.6 divided by my new standard deviation, and that will give me a value of, let's see, that will give me a value of negative 6.64, rounding to 2 decimal places. So here's my mean of 0, negative 6.64 will be down here. I want the probability of being less than that. Right, the probability that my z is less than negative 6.64, that's the area to the left. That's exactly what our table tells us. So let's look at our table now. So our z-score, again, was in the negative 6 range. Right? It was negative 6.64. And again, that is lower than this negative 3 value, so we get the probability is going to be 0.0001. So we see this probability is 0.0001, which would mean the likelihood of getting an average body temperature of 98.2 degrees is very, very low. So if that actually happened, if we got a sampling of 106 people and their body temperature was 98.2 degrees, that would be significant. the probability of it happening is low. So if it actually happened, that would be very significant. And so it turns out that the University of Maryland actually did such a sample. They got a body temperature much lower than 98.6 degrees. They found a sample mean of a group of 106 subjects to be 98.2. That means our original hypothesis that the body temperature is really 98.6 degrees must be false, right? If the low probability events keep happening, our original assumption must be false. This is the basis of what hypothesis testing is, that if we have a hypothesis and these low probability events actually happen, then our original assumption must be false. We'll talk a little bit more about that process when we get to it. Hopefully you found this helpful. Again, if you have any questions, please email me. We can Zoom office hours. I can create additional videos with other lectures. If not, I'll talk to you next time.